Bayesian regression faces a critical challenge, ensuring trustworthy uncertainty quantification. To address this, the authors propose TrustBayes, a novel optimization framework for Bayesian metalearning. This framework learns and quantifies unknown uncertainties in real-world engineering systems, such as autonomous vehicles and robots, to ensure mission success and safety. Bayesian learning, a class of statistical learning frameworks, models targets as samples from a prior distribution. It consistently approximates targets and inherently predicts with uncertainty quantification. However, existing works often assume structurally specified likelihood and/or prior distributions, leading to untrustworthy uncertainty quantification. Metalearning, a machine learning framework, utilizes data from multiple tasks to identify a good initialization or prior for the learning algorithm in new tasks. This enables fast learning with minimal data. The authors discuss existing works in metalearning, including those that consider generalization errors and Bayesian metalearning for neural networks and Gaussian process regression. The TrustBayes framework optimizes Bayesian metalearning models while ensuring trustworthy uncertainty quantification. The optimization problem involves identifying a good initialization prior for the learning algorithm in new tasks, formulated as an optimization problem with an objective function representing the expected performance of the adapted model. The authors analyze the lower bounds of the probabilities of the ground truth being captured by the specified intervals and the sample complexity with respect to the feasible probability for trustworthy uncertainty quantification. A case study using Gaussian process regression demonstrates the effectiveness of TrustBayes, outperforming the metaprior algorithm. Overall, TrustBayes presents a novel approach to Bayesian metalearning, focusing on trustworthy uncertainty quantification, crucial for real-world applications requiring high autonomy and safety. The proposed framework aims to provide a more reliable method for quantifying uncertainties in complex systems, enhancing their reliability and performance. Bayesian regression with trustworthy uncertainty quantification is a fundamental problem in machine learning, where the goal is to optimize prior and posterior distributions to capture the ground truth of a function within specified intervals with a pre-specified probability. To address this challenge, we propose TrustBayes, a novel optimization framework that leverages a meta-trained prior distribution and the posterior distribution to minimize an objective function. The TrustBayes framework is designed to ensure that the uncertainty intervals generated by the model have a high probability of containing the true function values. This is achieved by optimizing the prior and posterior distributions to maximize the probability of capturing the ground truth within the specified intervals. We derive lower bounds on the probabilities of the ground truth being captured by the specified intervals, providing a theoretical guarantee on the performance of the TrustBayes framework. Furthermore, we analyze the sample complexity of TrustBayes with respect to the feasible probability for trustworthy uncertainty quantification. Our results show that the sample complexity grows logarithmically with the desired probability, indicating that TrustBayes can achieve trustworthy uncertainty quantification with a reasonable number of samples. The TrustBayes framework has significant implications for applications where uncertainty quantification is critical, such as decision-making under uncertainty, model-based reinforcement learning, and Bayesian optimization. By providing a principled approach to trustworthy uncertainty quantification, TrustBayes has the potential to improve the reliability and accuracy of machine learning models in a wide range of domains. The authors approximate the functional optimization problem by parameterizing the spaces of mean functions M and K using neural networks and finite-dimensional basis functions. They consider parameterized prior mean function m theta with parameters theta and parameterized prior mean function k phi with parameters phi. This allows them to rewrite the problem as a minimization problem with constraints ensuring that the intervals I theta, phi, x, and E theta, phi, x, are large enough to contain the true function values with high probability. The authors introduce the TrustBayes framework, leveraging empirical estimates from a meta-dataset dmeta. They define O1 loss functions C1, x, and C2, x, to evaluate the performances of the posterior functions and estimate the probabilities and constraints. The authors derive lower bounds for these probabilities in Theorem 3.1, which can be used to approximate the original problem. The lower bounds are expressed in terms of empirical estimates and error terms that diminish with the size of the evaluation dataset and the number of functions in dmeta. The authors use these lower bounds to approximate the original problem with a new formulation in equation 4, which is the proposed trust Bayes framework. They discuss the feasibility and sample complexity of the problem, noting that the sizes of the intervals I theta, phi, x, and E theta, phi, x, can be arbitrarily large by choosing phi accordingly. In the context of high-dimensional statistical inference, understanding the sample complexity of feasible delta is crucial. Specifically, the lower bound of feasible delta is characterized by the inequality delta is greater than or equal to c, d, lane, n, 1/3, where c is a universal constant, d is the dimension, and n is the sample size. This bound is derived from the properties of sub-Gaussian random variables, which are essential in modern statistics and machine learning. Sub-Gaussian random variables are characterized by their tails, which decay exponentially fast. This property enables the derivation of concentration inequalities, a fundamental tool in high-dimensional statistics. In particular, the Bernstein inequality provides a tight bound on the deviation of a sum of sub-Gaussian random variables from its mean. The proof of Theorem 3.1 is built upon the application of the Bernstein inequality to the empirical process. By carefully bounding the variance of the empirical process and exploiting the sub-Gaussianity of the underlying random variables, the theorem establishes a tight lower bound on the sample complexity of feasible delta. This result has significant implications for the design of efficient algorithms in high-dimensional statistical inference. The novel idea presented in this work is the use of sub-Gaussian random variables to derive a tight lower bound on the sample complexity of feasible delta. The significance of this finding lies in its ability to provide a unified framework for understanding the fundamental limits of high-dimensional statistical inference. In this case study, the trust Bayes method is evaluated for its effectiveness in providing trustworthy uncertainty quantification for Gaussian process regression, GPR, when the prior distribution does not accurately reflect the true distribution of the target function phi. The scenario involves a mixture of Gaussian distributions and a Bernoulli distribution. The training dataset consists of 2000 functions phi, each with 20 inputs for training and 100 inputs for evaluation. The objective function j, theta, phi, is the negative marginal likelihood over the entire metadata set DTR. The results show that trust Bayes outperforms the metaprior method in terms of phi, xi theta, phi, x, phi, xe theta, phi, x, and mean squared error, MSE, for the posterior predictions. Notably, the probabilities of the true values of phi, x, falling within the constructed 90% confidence intervals are higher than the required inclusion rate of 0.9 when using trust Bayes, whereas they are lower when using metaprior. This comparison highlights the importance of employing trust Bayes to ensure trustworthy uncertainty quantification, particularly when the prior distribution may not be properly specified. The results demonstrate that trust Bayes provides more accurate and reliable uncertainty quantification, making it a preferred method for GPR applications where uncertainty is a critical aspect of the modeling process. In this paper, a novel Bayesian metalearning framework called trust Bayes is proposed for trustworthy uncertainty quantification in Bayesian regression problems. Trust Bayes formulates trustworthy uncertainty quantification as constraints on capturing the ground truths of the function by intervals depending on the prior and posterior distributions with a pre-specified probability. This framework is evaluated through a case study using Gaussian process regression, GPR, and compared with the metaprior approach. The results, shown in Figure 1 and Table I, demonstrate that trust Bayes generates larger 90% confidence intervals that capture most of the values of the functions, including those with larger variation, whereas metaprior generates smaller intervals and fails to capture the values of the functions with larger variation. Figure 2 provides a visualization of the distribution of the functions, with 10 random functions drawn from the prior distribution. The prior predictions by trust Bayes and metaprior are compared, highlighting the differences in uncertainty quantification between the two approaches. The paper concludes by summarizing the contributions of trust Bayes, including the formulation of trustworthy uncertainty quantification, the characterization of lower bounds of the probabilities of the ground truth being captured by the specified intervals, and the analysis of sample complexity with respect to the feasible pre-specified probability for trustworthy uncertainty quantification. The comparison between trust Bayes and metaprior in terms of posterior predictions over 10 sample functions is presented in Fig. 3, highlighting differences in predictive distributions between the two methods. Trust Bayes is known for its robustness in environments with unknown dynamics, as demonstrated. In contrast, metaprior focuses on the use of metapriors for generalization across tasks. The combination of these approaches can provide a comprehensive understanding of underlying dynamics. Safety of learning algorithms is also significant, with methods like smart forgetting and Bayesian optimization with safety constraints, ensuring the stability of the learning process. The use of metalearning for fast adaptation and the incorporation of implicit gradients further enhance efficiency and safety. The application of barrier certificates for ensuring the safety of quadrotor dynamics involves the use of mathematical frameworks to guarantee the stability and control of these aerial vehicles. This approach ensures that the quadrotor's movements are confined within a predetermined safe region, preventing collisions and other safety hazards.